Hi, everyone. Good morning, good afternoon, good evening, depending where you are. Welcome to today's ICorr Midlands branch technical webinar. My name is Ali Oskui. I'm UK ICorr Midlands branch chair, and it's my pleasure to host today's session on validation of current magnetometry inspection for pipeline corrosion assessment. Thank you all for joining. We have participants from all over the world across the energy sector, consultancy, education, and manufacturing. We greatly appreciate your continued support of ICorr technical events. Before we begin, a few housekeeping points as before. Today's presentation will run until approximately 4:35 UK time, followed by a dedicated Q&A session until 5. Please submit your questions at any time using the Q&A function. If time allows, we may also invite a few live questions directly from the audience. We encourage technical discussion and will endeavor to address as many questions as possible. With regards to CBD certificates are available on request through the ICorr Midlands branch, so you should send me an email submitting your request. Please note that only online participants who attend the session will be eligible for the CPD certificates. And please note that, as before, the session is being recorded and will be uploaded after the webinar to the ICorr Midlands YouTube channel. We encourage you to visit and subscribe to the channel so you can be notified of the new webinar recordings and access our previous sessions covering a wide range of corrosion-related issues and recordings. We would also be delighted if you could join the ICorr Midlands LinkedIn page, where we share the latest news of the events, updates, and anything that might be of interest to you. We are currently planning a webinar for the end of next month on integrity corrosion issues on hydrogen production. This is still to be confirmed, and once the details are finalized, we'll share the update through our social media channels, so still be tuned. And if this topic is not confirmed, we will let you know about the alternative webinar topic in due course. So with regards to today's webinar, given the importance of inspection of the buried pipelines, today we are exploring current magnetometry inspection, in short CMI, a contactless above ground technique for assessing buried pipeline corrosion, usually unpickable, without excavation or inline inspection tools. The session explains the underlying physics behind the CMI and elaborate on how the technique is used to quantify coating defects and metal loss. CMI will also be compared with established pipeline integrity assessment methods, including inline inspection, direct current voltage gradient, in short DCVG, and closed interval potential survey, or CIPS. So we invited Mark to present today following a recommendation from the ICorr Midlands Committee after members had the opportunity to hear him speak at a recent conference. As part of our continued focus on pipeline integrity topics, we are very pleased to welcome Mark to share information on CMI technology today. And Mark is joining us from Houston, the USA today. It's now my pleasure to introduce our speaker, Mark Glinka. Mark is the founder of EMPIT GmbH. EMPIT is dedicated to transforming the way pipeline corrosion is assessed, delivering innovative solutions that enhance accuracy, reliability, and efficiency across the industry. So the floor is yours, Mark. So first of all, I'd like to ask you to share your presentation. If you have any kind of introductory comments, please.
Yep. Hey, thank you so much. And just a little one. So I'm not in Houston yet. I will drive later to Houston. I'm in San Antonio right now, joining a conference. So it's 10 o'clock here. I just had my morning coffee and I am super excited about doing this today. And yeah, let's delve into it. I hope everything works. I'm obviously sitting in a hotel room and I hope that we have stable connection. However, if there's anything, speak out aloud.
Sure. But you shared your screen. I can see your screen now. Perfect.
Top. Great. So let's have a deep dive today on CMI, current magnetometry inspection. our value proposition is the contactless pipeline inspection from the Earth's surface. And my primary goal of today is that you understand what we can deliver and what we cannot deliver. So where the limitations are and how we are different to the kits we are very familiar in. So DCVG, ACVG, CIPS, whatever floats your boat, that would be the primary goal. I would like to just quickly talk about EMPIT because we are a relatively new company and give you a little rundown about what makes us special. Then afterwards, the deep dive about CMI, the technique, the physics, how do we do it, and then last but not least, the practical experience and the result verifications. So who is EMPIT? EMPIT is founded in 2015 in a very shady garage in Berlin. Actually, I founded it, and we were operating from a garage which was costing 150 euros a month, and it had no floating water, it had electricity, and our vision was to change how people think about pipeline integrity. And it was obviously a very beautiful vision for a quite shabby garage, but we had a lot of passion, and now we are around 100 employees operating from 6 offices around the world. So we actually also have one office in Houston, and yeah, we deploy CMI to now over 30 countries in the world. And just that you have an idea how the history is. So 2015, we got the idea, and 6 years later, we were more or less operational. So we are not so long in the market, and we have been inspecting last year around 10,000 kilometers of pipeline, and the demand is increasing. So in 2026, it will be more. We won a bunch of things. We are also certified now, so step by step. And yeah, we are working with a lot of big boy clients. And I would say, possibly some of them, but there's now way over 100 clients around the globe. If you scream out that you can actually do something what no one else can do in the market, you come at one point to the point that you really need to prove it. And what we did in Germany, we did a very big research project, and the goal was to have all survey techniques that are existing more or less in the world and make sure that we put them together, put them on real lines, put them on a lab, put them on a blind test to really know where the limitations of each of the techniques are. And our technique, CMI, was part of the bundle. And you can also download and read everything online. It is DVGW Research Project NAMIC. You also see the number over there, but I just wanted to give you some of the key findings and the key results over here. And it's obviously the most interesting stuff, the real field. So stuff that works in the lab, and we were really good in the lab, you need to really roll it out to the field, and this is a very, very big challenge, and we all know this. And we have inspected in this particular project 250 kilometers of pipeline, and we did in total 37 excavations over there. And obviously, we used the current ISO standards and the standards to validate whether cathodic protection was working, respectively asking, do we have active corrosion? Do we have a problem? Or is actually cathodic protection working and we all pacified and everything is good? And you can see we found around like 6,500 defects over there. And I hope it is working. Can you see my laser pointer now that I can share it?
Yes, we can see that.
Perfect. That's great. So we found around 6,500 features. And what the really interesting part is with our technique, we can tell, not dependent on the size, whether it's corroding or not. So it doesn't matter how big your gradient is. We can just tell you, okay, is it corroding or not? We don't have a limitation that, for example, CIPS has. And you can see that, roughly speaking, 80% of the 6,500 defects were actually not really accessible, because usually they had a really, really small gradient. And you can also see, and this is one of the key metrics on the outcome of this particular project, that, for example, our true positive rate is, roughly speaking, 95%, whereas CIPS has only 25%. So that are some numbers, and they are a shock. And they were a shock for me as well, because honestly, we just did our stuff, and I was thinking, we might be all right, and hopefully we survived the project. But I was relatively shocked how bad the standard over the line techniques are. And you can also see what happened, and obviously it needs to happen. So we found 3 corroding defects with metal loss, where you need to do your repair work. You actually have not the pipeline safety established at that certain point. But CIPS, for example, didn't even say that there was a gradient, so everything was fine. And this rose a lot of question, and this is also happening right now. So how good is our standard equipment actually working, especially to answer the question, can we find active corrosion with it or not? And it obviously always depends. So you will say, hey, Mark, DCVG, it's just a coding survey. That's absolutely right. And we know the limitations of every kit. However, I want to delve deeper into this number over here. And I just don't want to tell you, oh, we are so much better than everyone else. I want to actually give you my personal opinion why it is this way. And I want to give you a solution how you can really ramp up the quality of the standard kits. You can see that there is quite a lot of operators in this particular project. So it's just a selection of the operators, but they are more or less one of the biggest in Europe. And obviously it's a German project. So there was the entire market in Germany was over there and was present. The key questions for today. So first, obviously, we all want to know, how can CMI determine active corrosion? And I will explain it to you today. I already kind of addressed this. What can we expect from CMI? What are the limitations? Then the physics. And last but not least, also a bit more comparisons, that we really compare the signals, etc., not only the statistics. How does everything work? That's obviously the essential question. So it is very simple. We come to the site and we use a truck with a signal generator. And the signal generator, it injects an AC current into the pipeline. So we are not DCVG. And we use this AC current to then measure a magnetic field. So there's nothing special about it. That has been in the industry for decades. But what we are doing is we are using up to 100 different frequencies simultaneously. Why? Why so many? And in what bandwidth? So bandwidth, 2 hertz to 2 kilohertz. And why so many? With AC, you have always 2 problems. The first problem that you are having is you have the capacitive coupling, and the second one, you have the inductive coupling. So when we see it over here in the schematic, with one pipeline, this might be working when you just use 1 or 2 frequencies. But if you have complex areas, so we are working a lot on refineries or like congested areas where there's a lot of different pipelines running parallel, you will have current hopping over, creating other fields, and you need to know what you're doing. And because we use so many different frequencies, we can fit induction and we can fit capacity, and we use an inverse solver. And this makes us sure that we are only measuring the pipeline that is directly connected. And how do we measure it? We measure it with different toolkits. So our goal is always to have a coverage of 100%. So there shouldn't be a bigger river or something like that, or some inaccessible area, and we need to leave it out. This is usually where corrosion sits. So we really want to make sure that we survey along the line, and this is what the different tools are for. So they're just the carriers, and you can see it over here for the magnetic field sensor bars. So it's the same in every system. We are working now as well on an offshore tool. So the boat you have just seen on the other side, it obviously has the limitation that it cannot go into like very deep water, but the actual ROV, what you can see over here, and this is together with the German government and 2 institutions, so it's a funded project, this can actually go. And with all magnetometry techniques, you will always raise the question about the standoff. So how deep can you inspect pipelines? That's obviously not the right question. The right question is, how far needs to be your sensor bar away from the pipeline access? This is what we are thinking. And currently, we can inspect in a distance, so a standoff distance of 50 meters. So that actually means like we can inspect in Europe more or less every pipeline. And we have obviously problems with offshore pipelines because we cannot boat, and then the pipeline is, I don't know, 200 meters deep because the seabed is 200 meters deep. So we needed to find another solution. And this thing here can dive then up to 2,000 meters, and you don't need to get rid of marine growth. And this is, for example, as ICorr is operating out of the UK, one thing which could be also handy for the subsea lines in the UK. However, like myself, I've always been someone who wants to push the industry and give you a vision. And you saw the drone, and drones are cool, but drones are heavily regulated. And for us, we don't want to survey in the rain. We don't want to survey where it might be insecure or you can get into real problems. And so I want to introduce where I see the future of surveying. And we have been working now on something or somehow a new robot, which we call Flux. And Flux is a robot that is supposed to inspect pipeline as a quadruped robot. So you can actually see it works fully autonomously. So it will find the pipeline autonomously via our magnetic field sensors. So it doesn't need any like orientation where the pipeline is. It will do it itself, and it will deliver corrosion for you. And this is how we can scale up the company. It is so hard for us to find good field personnel. And this is, for me, the vision. And you can see what we have been building here. Is it working perfect? No, definitely not. But the first iPhone was also not perfect, but it has changed the way how we deal with phones. And this is, for me, the iPhone moment. And this is, for me, how we will be scaling the company in the future. Some limitations. You can actually see over here what I already told you. So the max pipe depth, that's the standoff, is around 50 meters. Other than that, there is like our classical like restrictions. There is not really anything. There is just one thing which is really important, that our technique is working. We need to have first the galvanic connection, so established via CP, for example, or some gate valves, so that doesn't really matter. But the pipeline needs to be conductive. So we can inspect like spun iron, cast iron, gray iron. When it comes to water operators, we can also inspect dead legs. So that means the line is not in service. We can inspect the steel lines, but we cannot inspect polyethylene lines, for example. So this is one really big limitation, and we cannot work around it, because if the current is not getting into our pipeline, we cannot generate the magnetic field. Alrighty, so when we look at what we are doing, is obviously not only corrosion, what EMPIT is doing, it's the one-stop solution that we are trying to establish, because one really tricky thing is, and I think some of you really know how nasty that can be, to align data. If you align inline inspection data, then DCVG data, then depth of cover survey data, and you try to align it just in positioning, it's a heck of work, and you possibly will never be fully confident if this is now right what you can see there. And so we have high resolution GPS antennas, and we can also give you the 3D position of the pipeline, the bending strain. So we are digitalizing a lot of stuff at the moment. And when you think about the bending strain, this is then needed for hydrogen conversion, so the H2 readiness. We have been converting several lines now in Germany because it's a very big topic over there. But it's also just creating digital twins, and becomes so important that we got jobs for really now transforming the underground of an entire city to a digital twin. So this is digitalization. Then we have the methane emission. That's now also a EU regulation, and we are working on that. So when we survey the line, why not measuring the methane concentrations? But we are going to focus on the coating defect localization and the corrosion assessment today. Very important. All of this here can be recorded in one single path. So just with one inspection run, we record this data, and you don't need to send us 3, 4, 5 times over the line. We will just do it with one single hit. How does everything work? Okay, now the insights I'm going to share here. We have actually started to think we use one magnetometer and we get the full readings. And this is what I mean, to have something in the lab. This might work, but we learned very fast that we cannot just have a multimeter like for 10,000 euros with a bit of tweaks there and here. We really need to build something which is high performing and which is unfortunately also quite costly. And so we have systems so that are 3-dimensional magnetometers with up to 70 sensors. And this is what you would need. And that's the first big hurdle you want to overcome. You want to establish, when you measure magnetic fields, you want to establish a really good signal noise ratio. And you want to know what you measure, and you want to measure it in the range where magnetometers are working well. And so we are using up to 70 sensors in one array, and we are capturing the 3D magnetic field. And this is then the key, so that we are having the vector component of the entire field, and then we can see like what certain signal is in what certain dimension of the signal. When we walk over the line, this is just how it looks. We generate a magnetic field. We have the isomagnetic field lines, and then we have an inverse reconstruction where we are constructing the path, the track, the route of the pipeline, whatever you want to call it. And then obviously we get the geometry, so we get the bends, bend radii. And that's, for me, the premise to really get a good reading on corrosion. Just imagine you have 2 gradients you're measuring, and they are the same amplitude. And one time your pipeline is 1 meter deep, and the other time the pipeline is 10 meter deep. That is a completely different world. And you need to feed your algorithms, you need to feed your ideas this specific depth of cover in order to really move on and not find only coating features, but really find corrosion. And we feed our solvers, so our AI agents, all this information. So what's the outcome then? The outcome is that as we are walking, boating, droning, whatever over the pipeline, we are not limited to the classical probe spacing. And probe spacing, I mean, let's think about, for example, DCVG. We usually use a probe spacing between 1 meter and 5 meter. And you can see we have a measurement grid of 1 centimeter because we are sampling with 20 kilohertz, and we just have seamless data, so continuous data, which is really key to then at the end deliver corrosion rate. You can see then with the LiDAR and with the radar, we give you the 3D profile of the pipeline. And as I said, so this is, for example, an area where there's a lot of mining going on. So the pipeline has been moving. We can create the 3D models over here. And this 3D models will then help you also to understand what's beneath the ground. When we think about all of the classical systems, the old school systems, I would call them, they just measure one component, and that's the Y component of the field. Why? Because it's easily accessible, it's quite cheap to get, and if you look online or ask your AI, this is the absolute standard. So how you would possibly think about a pipe finder or anything like this, how you would determine the B field, the pipe depth, the current in each of the frequencies. We have learned now that we are using three-dimensional magnetometers, and so we only cannot look at this Y component, we can also check other components. And what we were seeing at one point is then when we are having a low resistance conductivity between the soil and our steel, so the metal, we are generating an X field. So this is what you can see over here, but it's only present when we have this low resistivity, meaning we have a coating defect over there, and the current will go back to our grounder. And what is so interesting about it? The most interesting part is that when you know the current in each of the pipelines, that is very standard. You know the interval is the voltage, so you just integrate it. You can use ohmic law, and then you will have the resistance. But you not only have the resistance, let's say with Renner 4 probes 10 meters away from the pipeline, you have the resistance of the bedding directly over here at the interface. And this is what we thought a very good idea to elaborate on it and to really delve deeper into it, because it opens up that you can find corrosion. What is happening afterwards? Afterwards, we are using, it's called a deep fusion AI neural network. So it's more or less classic now in any signal progressing in order to determine the different signals. And this is how the signals are then looking when they are pre-progressed with the solvers. So what do we see over here? So this is our data evaluation program. We are looking at a stretch, like, let's say, that's roughly speaking like 70 meters long. You can see here is a pole from an overhead power line. This is how it looks. So it's just plain field. And the question is always, when we have power lines in parallel, is there any AC corrosion or what's going on? And that was also our task here in this particular line. So the plots, they show you the x-axis over here, and they show you the X field. So you can see this is the arbitrary value, and this is the real component of the signal. And here we are just fitting the current. So with all three coating features, what we have, so all this like vertical red lines is a coating feature. That means there's a coating defect. We can see that we are losing a little bit of current. And for example, here it's the clearest. So let's say we have established like 1.45 amps, and afterwards it drops to 1.42 amps. So over here. So that's very clear. Okay, there's nothing really revolutionary in it, because you can see it's seamless data. This is quite cool. And then we have built a highly detective tool in order to find small coating features. That's great. But the real value prop is, which of these three features is corroding? And I will give you now a full rundown how we are doing it. And at the end, you will learn which one of the three is corroding. Alrighty, so what did we do? We were actually studying a lot of literature, and we were also then going to San Diego, because this is where Mr. R.J. Kuhn is from, so more or less the inventor of the minus 850 volts potential criteria. And we have been reading and then really studying a lot of his publications. And it was as early as 1930. And this is a quote. He says, long-time tests have shown, as previously stated, that after several months, a depolarization sets in and the galvanic difference of potential is again restored. When this takes place, the extent of corrosion is probably a matter of the formation of, attention now, protective films over the surface of the anodes. Should proper attention films form, corrosion will probably cease, while should it not form, we see no reason why the iron should not continue to go in solution from ordinary electrolysis caused by galvanic forces. Okay, so this dude actually managed already in 1930 to see when we have proper films that we have no problem, whereas when we don't have passivation layers, we do suffer or may suffer active corrosion. So that was for us the big bang, and we were thinking, oh, maybe we can measure this in the lab. And you can see the data over here. So we have 3 frequencies. Obviously, the normal signal contains up to 100 frequencies, and we see we are losing current at each of the frequencies, and we have this nice little zero crossing. What we can clearly see, let's say this blue line is 2 Hz, whereas this greenish line here is 2 kilohertz, that we do have an attenuation dependent on the frequency. So we have a frequency spread. The highest frequency is losing the most amount of current, whereas the lowest frequency is losing the least amount of current. So what do we need to do electrochemically to actually have this behavior? We need to build in a capacity in the system, and the capacity goes with the frequency, and our capacity is our soil to steel interface. So that's our protective layer. So actually we can see, dependent on the capacity or on the spread resistance and the difference of the spread resistance for each frequency, if we do have this passivation layer or not. So over here we know, let's say it's a calcareous deposit, it will obviously cause an attenuation in the lower frequencies. We can see this directly. Let's now go to the second case, and you can see what is changing. The frequency spread is more or less gone. Think about AC corrosion, for example. AC corrosion is a chemical active progress, and it will make your pipeline corrode very fast. When you dig it up, you have this shiny metal over there, and obviously that's not possible that any protective layer will form over there because it's going to get destroyed by the AC interference what we are having. And so you can see we then measure no frequency spread. So difference, we have a frequency spread. We can all go to sleep. Cathodic protection is working well. We have no active corrosion. Then, okay, we have no frequency spread over here. We know that we need to take further measures. Okay, so let's look now into this graph again. We have 3 spots. So we can clearly see, if you analyze the first 2 spots over here, that there is this frequency spread. Here's the frequency spread. Here, well, it's quite gone. And this is raw data. This is not even really progressed, right? So there's not any magic in it. You can then see that when you see the signal over here, when they dug it up, we have a beautiful corrosion spot, what we are looking for. And here, for validation purposes, they just dug up another spot. And you can see over here, there's a growth welt, but there's actually no corrosion. And now we obviously need to address the question of money and return on invest. So what can we then deliver? We can clearly tell you, dig up this spot, but don't dig up this spot. And out of, let's say, 600-700 defects, what we find in the pipeline, we can tell you, you don't need to have any unnecessary excavations. You can save cost. And the third feature here, you don't need to dig up. And so you save a couple of grand. And this is exactly what they did. So they were digging up this spot, and they were digging up this spot. All right, so there's a lot of specification about us. The only thing I want to just quickly elaborate on is the probability of correct yield status determination, corrosion versus passivity. Like in the study came out that we at least at 80%. So that actually just means that our stuff is not working perfect, but you can rely on it. And we are obviously getting better over time. All righty. Practical experience and result verification. So this might be a bummer for most of you who have listened in because you thought, oh my goodness, this is so revolutionary. Why didn't I think about doing this? This is so cool. And like, let's be honest, CMI is not a really new method. So we do have changed the way how to address certain topics, but we are not reinventing physics over here, just to be clear. What we do now more and more is we anchor ACVG and DCVG into CAM, so current attenuation measurement. This is actually what we are doing. So we are measuring a B field and the attenuation of the signal. So CMI, let's say, is CAM. But because, for example, for ECDA procedures, you need at least two independent survey techniques, we just mix them wildly up. Do I believe in ACVG and DCVG? No way. Like, not like for like finding coding features, yes, but for really assessing pipeline security, no. And this is the reason why all of the big operators in the world ditching, for example, ECDA at the moment, because you just have so many unnecessary digs and you never really find corrosion in your pipeline. You just see, is the coding good or not? And I don't know what I should do with this information. I don't care about the coding. I care about problems, and that's metal loss. All right. So I promised you in the beginning to tell you that I will give you a solution how you will find more defects. And this is now what I will do. You can see here, this is like what a study what we have done in the US, and it's a line they just freshly put in with 15 defined defects. And the primary goal, one of the primary goals of this survey was how accurately can DCVG and ACVG spirally separate defects, and how much is interpretation of the results based on the experiences. And I'm still, I would say, a young timer in this industry, and there's so many people who are doing this for 30, 40 years, and they always say to me, hey, yo, Mark, like I have 30 years of experience. I know where corrosion is and where not. And my background is like economist and math. And I'm also saying like, okay, how do you do it? Explain it to me. And they explain me, oh, it's so much experience. So how will I scale an industry which is dealing with critical infrastructure in a way that I know, oh my goodness, when this guy is retired, he cannot pass on knowledge because I need at least 30 years of experience to understand what I'm doing. How am I going to do this? So obviously, like, we want to have a reliable tool which is ideally working independent of the operation of people. And we are talking now about the measurement point density. You can also call it probe spacing or spiral resolution, whatever floats your boat over there. What you can see over here, so we have this pipeline, 15 defects, all this horizontal dotted lines. One defect, that's the position. So we have the position along the route. We have DC, so that's our DCVG, and we have 4 ACVG frequencies, and the people were serving behind each other. So we have this nice little zero crossing where a defect is. When we measure with an interval of 5 meters, we find 4 out of 15 defects. And now let the magic begin. When we survey with an interval of 2 meters, you can actually see, okay, we are getting there. So 9 out of 15. So not bad, more than half, great. When we are surveying with the interval of 1 meter, okay, that thing is becoming somehow something we can rely on. So we are just missing, let's say, 15 to 20% of the defects. And if we are then ramping it up to an interval of 10 centimeters, so you can also see that you then have continuous like signal and your curves are looking much more beautiful, you're detecting 13 out of 15 features. And that's great. So actually we come from 26% to 86%. And now the problem is, possibly most of the people know this already, but we are losing a lot of productivity on site. So for a test of 60 meters, this is obviously possible to do. But if we think now about we want to survey a pipeline being 20 kilometers long and you need to have a probe spacing of 10 centimeters, it's going to be a very, very big challenge because it's going to take many weeks possibly. So the idea for the industry, in order to really first and foremost make ACVG and DCVG finding defects, we are not here and we're talking about corrosion assessment, is for me that you are actually cutting down, or like, let's say, making sure that your probe spacing is as small as possible. And this is now the explanation why I think you need to find every defect, and I will explain it to you in very simple words. So defects which are not corroding, they have an enhanced pH value, let's say above 9. And they will have nice amplitudes over here with your signal, because we know when you measure with your gradient, pH value goes up, spread resistance goes down, gradient goes up. So they are beautiful, cathodically protected defects. But we are actually interested in the defect where pH value is low if we are in the DC regime. So like, let's say near neutral, where we know spread resistance is possibly higher because of pH value being lower and your gradient is really small. So we are actually looking in this signal for the tiniest of the tiniest feature in order to find the ones which are corroding, not for the big boys, because the big boys over here with a big amplitude, they're perfectly cathodically protected. And this is also, when you look into the statistics, and OGE, that's the biggest German operator, they dug up over 200 features based upon amplitude and based upon the IRF potential. And they found more or less nothing. They found one spot which they thought it's actively corroding. It can be also coincidence, but it actually shows the problem of the industry, what we are having here, if you look at the signals, that it's going to be very tricky to actually look at the amplitudes only. We are interested in the small defects, and we will see the small defects if we have a relatively small probe spacing. That's the last two slides, then I'm done. There's always coming the question, okay, where are you working, Mark? And like I say, okay, we work also a lot in like complex areas, so a lot of airfields, airports, and it's becoming more and more because we are not dependent upon the ground conditions. So the soil can be sealed. It's regardless for a system. So it doesn't really matter. You can see all these little lightning icons over here. That's the coding features. And you can see this is a CIPS measurement. And when we hit the runway, our signal is going bananas because it is obviously high resistant, the runway. And so I just want to show you that this is possibly also the reason why we work a lot in urban environment, a lot in complex environment, because some data is better than no data. So when you cannot ILI the lines and you cannot use any smart picks or anything like that, you want to have a solution. And I want to finish this with the biggest limitation that CMI has at the moment. It's we can talk about corrosivity. We can tell you it's active, and we can obviously also tell you it's passive. We get better and better with corrosion growth rates, so we can tell you also how many micrometers per year you will be losing. But we cannot tell you the absolute wall loss. We are not a flying pig. It's not possible for us to actually tell you, hey, here you have 25% metal loss, here you have 18% metal loss. Think about it as if you think about a speedometer. So you see the actual speed, but you don't see the distance that has been traveled. And this would be it for now. Thank you so much for all of the attention, and yeah, happy to receive questions. Ooh, wait, I need to find the slide. So here it is.
Thank you, Mark. If you can just show the last slide of the template that I shared with you with the social media. Or
Yeah, it should be
okay.
actually there right now, is it?
So, but you are not sharing right now. So, okay.
Oh, wait a second. Sorry.
No worries. I'll continue, then you can put it up. So thank you very much. This was excellent, futuristic, and insightful presentation. Well done. But personally, I don't like those robotic dogs. I prefer, real dogs to do that. So if you can, uh, you can employ those dogs in order to do the inspection, that would be better. Okay. So we'll now move on to the Q&A session. Please feel free to share. So as I could see, there are many questions, but feel free to share any questions that you have. We can, if we have time, we might be able to take one or two questions, live questions. But if you raise your hand and open your mic. So I try to use Copilot to just, organize the questions. So if I miss anyone, just I apologize beforehand. So first I start, if you keep the answers short, then we can cover more questions. I would
I
appreciate.
try.
So from an anonymous attendee asking, of the 37 verification, I think these two were found to be false positives. What rationale is there for these false positive in this initial assessment? I think he refers to one of the slides that you showed about the accuracy of the measurements, if you remember. So he said, yeah, okay, we
I
can
think I
ask.
know. So, like, I also know what this is addressing. Okay, so the thing is, like, this is possibly always a good reason. So, when we think about the capacitive layer, capacity is not there and then it's gone. So, it's, let's say, when we also fit it in very simple terms, it's a linear progress. And you need to always assess when something is critical and when not. And from our standpoint and our view, we always were thinking, okay, if we measure a very small capacity, we will have the reason to think that we have active corrosion. But this threshold is, for example, also dependent a lot on the soil. And so now this is what I explained you. We put in spread resistance and everything. And we also learned a lot through the DCVG project, because that's what it meant for, that we also understand the limitations and specifications of our system. And these two, there were like, obviously there were faults in terms of what to expect, but we were conservative. So what we said is, look, there is active corrosion, and we always give a class where we say how certain we are. And the class was 3, so that's the highest uncertainty level. They dug it up. They didn't find any metal loss, but we were also seeing a relatively high capacity, or like that the spread resistance, to put it in other words, was like a little bit changing between the frequencies. And what we want to see, and this is the last bit because it's really important also for understanding our technique, we want to see between the interface of steel and soil that there is no frequency dependency. Whereas when you look at the remote Earth, this never has a frequency dependency. And this is the reason why we really just see this certain interface. And we are constantly learning. And I would say it's always about like thresholding, or like, boxing your system for the right conditions in the right moments.
Okay. Thank you very much. If we can keep because I have many questions. Sorry to get.
Okay.
Your methodology is very simple. It just reminds me of electrochemical impedance spectroscopy. But anyway, yeah. So we have a question from Vasim Sabir. Can CMI measure buried lines, internal corrosion, or can it calculate thickness loss? You alluded to that in your final slide, but if you can elaborate on it, I would appreciate it.
Sorry, can you, what was
can CMI measure buried lines internal corrosion, or can it calculate thickness loss?
Okay, so that's also something, obviously we always need to establish like contact between the electrolyte and the pipe. So very simple answer, no, we cannot measure internal corrosion. With our principle, we can also not measure it in the future. I'm quite clear. What I would say, because we have found it, we found a bunch of stress cracking corrosion. So that is possible, but we cannot classify it. We are working on it. And for the last bit, we are not a flying plick. So we can, and we are getting better and better with corrosion growth rate, but we will not be capable of telling you this is 30% metal loss.
Okay, thank you very much. One question from Zubair Ibrahim Saib. So for the CMI ROV, have you trialed it on site? I assume current and waves will affect the alignment. How much is it affected by that? So I mean the waves.
Yeah,
And, yeah.
I got it. No, we have done it, and also like in the lab, we have created some waves. And the good thing is, look, we have two IMUs in the system, and if we can carry the system, it's ultra shaky. And if we think about an ROV, the waves what you are having, they have a lot lower frequency. So actually, this is no problem. The movement of the ROV with the waves or the current is very simple to solve. But what is really hard to solve, if you are just running over the pipeline, you are actually having a quite high frequency. And we have solved that with like putting two IMUs in our systems.
Perfect. So we have another question from Nathan Dapa. How does pipeline depth and land topography affect measurement? You mentioned that, but if you can a little bit elaborate on it.
Yeah, so like we are completely independent of the soil and we have a normalized signal. So when we think about DCVG, you measure with different resistivities the soil. So let's say you measure in autumn, winter, or spring, you will get 3 different readings because your signal is always a wild mixture between your electrodes plus your ground resistivity plus the soil resistivity, etc. From our side, we are completely normalized. So we have amplitude, we have phase, we know the amplitude of the current source and the phase of the current source. And then obviously the tool knows it as well. So we can get rid of all influence of remote Earth, and it doesn't matter. So we are measuring in the driest condition in the world, in the desert, we are measuring in the swamp, and we are measuring on sealed ground. So in very simple terms, you can send us where you want. It doesn't matter how the soil resistivity is.
Perfect. There is another question from Zubair, but I found it very interesting, so I'd like to ask you. So can CMI be used for sleeved or jacketed pipelines? So pipe-in-pipe system.
Yeah, so it can. And we had a recent case actually also in the US. It's always the question, what do you want to inspect? If you have pipe and pipe and you want to like inspect the outer pipe, it's going to work. If you want to know something about the inner pipe, it's obviously not going to work because it's completely shielded. So it's the same with casings. That's also one limitation. When we think about casing and you have pipe and pipe, our magnetic field is going to be shielded. But what we can tell you, and this is also what we did over there, that the outer pipe had also a severe problem, and this led to finding the fault in the inner pipe. So that's always what I say. Some data is better than no data. It's simple physics behind it. So jacketed pipes, they're possibly not working in the future because that's the restriction of magnetometry. But we can actually correlate data. And in this particular case, it has worked really well. And they have been using 5 vendors before of us. And we were actually the first one solving the problem.
Perfect. There's a question from Selva Kumar. So he's asking what's the difference between SCT surveys and CMI surveys? I don't know. I'm not sure what does SCT
Yeah, I
mean.
think I know. Yeah, SCT
Okay.
is passive magnetometry. So
Okay.
it's stress concentration tomography. And the difference is what it actually says. So let me answer this. SCT, MMM, MTM, LSM. They are all the same. What they are doing is they are measuring the stress concentration zones that are because of the Earth magnetic field. And how it's in very simple terms working, we say, oh, we have a stress concentration zone, and this leads us to a problem, but the Earth magnetic field, so it's passive magnetometry, is actually the root cause. What we are doing is we are doing active magnetometry. We are injecting an AC current into the pipeline, and we have amplitude and phase. With passive, you more or less have no orientation where you are. You are absolutely dependent on the vector of the Earth magnetic field. And in some cases, it can work. This is the reason why it exists in the industry. But to actually make it reliably work, I would say we need to do active because there we constrain our system quite well, and you cannot constrain the Earth magnetic field.
Perfect. Thank you very much. There's a question from Vasim again with regards to the coating. So, for example, does your technique can detect, coating defects within 3-layer coatings like polyethylene
Yeah,
coatings or
that's no
fusion bonded
problem.
epoxies?
Yeah,
Yeah.
so that's no problem. So we are actually also sitting a lot on very new pipelines. So just to make sure, when they're freshly commissioned, that everything is good. So 3-layer polyethylene, FBE, bitumen, old what patches, that doesn't matter. There's also a lot of publications online from us where you can see that we have a wild mixture of coating applied and still CMI performed over there. So in very simple terms, the coating doesn't matter. It doesn't influence the quality of the system itself.
Okay. So we have one interesting question from Salim Yarabi. So uh, basically, he wants to know the effect of cathodic protection. This is a question that I also had. So what's the effect of the cathodic protection and the the applicability of your
Yep.
technique to?
So obviously what we want to do is we want to either mimic the cathodic protection on potential that we establish it how the way it is, or we just leave it on. What we don't want to do is we don't want to change it, because if we are changing it, we are changing the concentration of OH minus, which is close or at every feature, and we kind of have a problem to assessing if this bad boy is corroding under the certain conditions. So what is really, really important is that we are not changing the system at all, and we are measuring under the conditions. And this is, for example, like obviously it's super easy to just ramp up with DVG, like with just the gradient measurements, the voltage. But what you're going to change is you're going to then change the OH iron concentration, and this will mislead and you get a different state. So from our perspective, we do two things. Either we mimic the cathodic protection when it needs to be turned out for whatever reason, or we just say, hey, you're good to go. We just apply our AC current, and then we are working under cathodic protection how it is, because this is the way how you find corrosive spots as they are, and not just how we made them.
Perfect. I think we can take 2 or 3 more questions and then but sorry for because I receive more and more questions. But one, I wanted 2 questions together. So one audience asked about the effect of parallel pipes. So if you have closely spaced parallel pipes, and also the other one about the AC interference. What are the
Yeah.
effects on?
So
Yeah.
that's a good one, and that's a really nice question, because there is now also like two big publications coming up with big operators, and they are addressing exactly this. So the first, just say we have piled pipes that they, let's say a refinery or like the jetties, or like you have 20 parallel pipes. Can we work? Yes, we can. We're inspecting air bases, we're inspecting refineries. So there's a lot of pipes in very, very close spacing. So the wall-to-wall distance can be 10, 15 centimeters. Our technique still works. This is what I explained why we are using 100 frequencies. The second one, and this is also something which is important when we think about stray currents or AC interference. Is our system sensitive to it? No, it's not. And the reason why it's not is because we choose the frequencies in the way that we have an AI running. We know the harmonics and we know the signal itself. And we are making sure that we are not getting disturbed by the, let's say, 50, 60 hertz frequencies or the rails. So the beauty of the system is we can work, let's call it, in congested areas, no matter how high the AC induction is, no matter how high the stray current is. We don't have a wiggy-woggy off potential. We can just deliver results.
Perfect. So we should come to bring the session to the close because we are running out of time. So if you just bring your email slide back, because some of the audience wanted to see your email address in order to have some
Ooh,
sort of
yeah,
questions.
now you're.
So I ask all the audience if they have any questions. I just capture all your questions. We can share it with Mark, but you can also contact him. So thank you very much for your time. On behalf of the ICorr Midlands branch, I would like to thank Mark as well for his time. He's on on a journey and on a trip to the USA. So he took basically we used this opportunity to have him on board for this webinar. Thank you very much for your presence. I hope you find today's webinar was informative and relevant. And please keep an eye on upcoming ICorr Midlands technical events in our social media channels and webinars. And we're looking forward to see you again in near future. Thank you once again and have a good time.
Thanks for everyone joining. It was a pleasure.
Bye.